Today, a magnitude 4.2 earthquake struck at the exact junction where two of California's most dangerous and overdue fault systems meet. Under normal circumstances, a 4.2 is not a significant event. It rattles windows, it shakes shelves, it does not make international headlines. But this one is different. And if you understand what is sitting at that junction, what has been building there for decades, in some cases for centuries, then you understand why seismologists are paying very close attention to a number that most people would dismiss. Subscribe and turn on notifications before we go any further. Because what is happening in California right now is not one isolated event. It is a sequence. And that sequence has been building for longer than anyone alive has been watching. Let us start with the location, because it is everything. The earthquake struck at Frazier Park, California, at a depth of approximately 13 kilometers on July 12, 2026. The precise epicenter sits at the junction where the Garlock Fault meets the San Andreas Fault, one of the most geologically complex and stressed intersections on the entire west coast of North America. The San Andreas Fault needs no introduction. It is the 800-mile boundary between the Pacific Plate and the North American Plate, capable of producing magnitude 8 or greater earthquakes, and last ruptured in a major event in 1857, 169 years ago. The Garlock Fault is less famous, but equally dangerous. It runs roughly east-west across the Mojave Desert for approximately 250 kilometers, connecting the San Andreas to the fault systems of the Eastern California Shear Zone. It is a left lateral strike-slip fault, meaning the ground on the north side moves westward relative to the south. And here is the critical detail. The Garlock Fault has not produced a major rupture in somewhere between 500 and 1,000 years. 500 to 1,000 years of accumulated stress, with the capacity for a magnitude 7.5 or greater earthquake, sitting at the junction with the San Andreas, which is itself at its highest stress level in over a millennium. And today, for the first time in at least 26 years, an earthquake of this magnitude struck precisely on the junction. The USGS database for this specific section of the fault, going back to the year 2000, shows only 2 earthquakes above magnitude 5 in that entire period, a 5.2 and a 5.1, both occurring in recent years. Below that, a handful of magnitude 3s. The 4.2 today is the only earthquake in 26 years to strike exactly on the fault plane at this junction. Not nearby, not in the general vicinity, on it. That specificity is what matters. Now let us understand why this junction is so geometrically significant. Where the Garlock Fault meets the San Andreas does something unusual. It bends. The fault line, which runs roughly northwest through most of California, curves at this junction, and in fault mechanics, bends are where stress accumulates most intensely. The rocks on either side of a bend cannot slide past each other as freely as they can along a straight fault segment. The bend creates a mechanical lock, a point where energy builds and builds without release. This particular bend has not released in a major earthquake in the historical record. The last large event anywhere near this junction was the 1952 Kern County earthquake, a magnitude 7.5 that struck on July 21, 1952, at a depth of 6 kilometers. And even that event occurred not directly on the junction, but to the north of it. Before that, in 1812, double sequence produced earthquakes of magnitude 7.5 and 7.1 in this general region. 160 years without a major rupture directly at this stress concentration point. And the bend in the San Andreas means that every year without a rupture adds more stored energy to an already critically loaded system. To understand the full picture of what is happening in California right now, we need to talk about a sequence of events that began not in July 2026, but years earlier. In 2019, a magnitude 6.44 shock struck the Ridgecrest area on July 4th, followed the next day by a magnitude 7.1, the strongest earthquake to hit California in more than 20 years. The Ridgecrest earthquakes occurred in the Eastern California Shear Zone in the Mojave Desert, east of the San Andreas Fault. The scientific analysis that followed those earthquakes produced a finding that seismologists consider extremely significant. The Ridgecrest sequence increased the static stress on the Garlock fault by approximately 30%. That is not a theoretical projection. That is a measured calculation based on the geometry of the fault systems and the physics of how seismic stress transfers between connected fault systems. Think of it this way. The Garlock fault was already loaded with centuries of accumulated stress. Then a major earthquake to its east transferred an additional 30% of stress onto it in a single day. And then, in the weeks following Ridgecrest, the Garlock fault began to creep. GPS sensors and radar satellite measurements detected the Garlock fault moving at its surface for the first time in recorded scientific history, not rupturing, not producing a large earthquake, but slowly, measurably sliding, a sign that the stress on the system had reached a level where the locked rocks were beginning to deform. That slow creep has since stopped. The fault locked again, but the stress that caused it did not go away. It is still there, augmented now by years of additional plate motion since 2019, and today punctuated by a magnitude 4.2 precisely on the critical junction. Now, in June 2026, a research team published findings showing that the San Andreas fault system has reached its highest accumulated stress in over 1,000 years. We covered this research in detail when it was released. The study identified a specific mechanism called the earthquake gate, a junction known as Cajon Pass, approximately 80 kilometers northeast of downtown Los Angeles, where the San Andreas and San Jacinto fault systems meet. Under current stress conditions, the researchers concluded, a rupture starting on one fault system could propagate through Cajon Pass and simultaneously trigger the other, turning what would be a single major earthquake into a cascading multi-fault rupture with a combined magnitude of between 7.4 and 7.8. That research focused primarily on the southern San Andreas and the San Jacinto fault. The Garlock fault adds a third dimension to this picture. The Garlock intersects the San Andreas at the northern end of the most critically loaded section of the fault, essentially sitting at the top of the zone that the earthquake gate research identified as the highest stress concentration in California. A rupture beginning on the Garlock fault, or a Garlock rupture triggered by a San Andreas event, could affect a much larger geographic area than either system alone. Let us be specific about what a Garlock rupture would actually mean for the people living in its path. The Garlock fault runs east-west across the northern Mojave Desert, passing north of the cities of Lancaster and Palmdale, communities with a combined population of over 400,000 people sitting within direct reach of its rupture zone. The shaking from a magnitude 7.5 Garlock event would be felt across an enormous area, from Los Angeles in the south to Bakersfield in the north, from the coast to the Nevada border. But the Garlock fault's most dangerous characteristic is not its own rupture potential in isolation. It is what a Garlock rupture could trigger. The stress transfer from a large Garlock event onto the already critically loaded southern San Andreas would be immediate and significant, potentially the final nudge that pushes the San Andreas past its own failure threshold. Scientists describe this as a cascade scenario. One fault ruptures. The stress it releases transfers to an adjacent fault that was already near its limit. That fault ruptures. The stress transfers again. Each event in the sequence makes the next one more likely, not less. California's fault systems are so interconnected and so uniformly stressed right now that a cascade scenario, multiple major ruptures in sequence over days, weeks, or months, is considered by researchers to be a realistic possibility, not just a theoretical worst case. The historical record suggests this kind of coupled rupture is not just theoretically possible, it has happened before. In December of 1811, a major earthquake struck the New Madrid seismic zone in the central United States. The sequence continued through the winter of 1812, producing multiple large earthquakes over several months. In March of 1812, directly in the middle of that New Madrid sequence, a double earthquake struck Caracas, Venezuela, producing magnitudes of 7.4 and 7.1 and causing catastrophic destruction. These events are thousands of kilometers apart and geologically unconnected, but they are a reminder that major fault systems can produce clustered sequences across a region and across a period of months, not just in single isolated events. This year, on June 24th, Venezuela experienced its most powerful earthquake sequence since 1900, a double rupture of magnitude 7.2 and 7.5 within 39 seconds. On the same calendar day, a magnitude 5.6 struck near Willits in Northern California, the largest earthquake recorded in that specific area in the modern seismic record. Weeks earlier, a magnitude 6.0 struck the Gulf of California, directly on the fault system that feeds into the southern San Andreas. And today, July 12th, a magnitude 4.2 struck exactly at the Garlock San Andreas Junction for the first time in 26 years. Each of these events, taken alone, is manageable. A 4.2 is a minor earthquake. A 5.6 is a moderate one. A 6.0 in a remote offshore location causes minimal damage. But taken together, across a fault system already identified as being at its highest stress in over a millennium, in the context of a year in which major seismic events have occurred in Venezuela, Japan, the Philippines, Papua New Guinea, and Nicaragua, the pattern demands attention. Seismologists are careful about the language they use, and rightly so. Earthquake prediction remains beyond the capability of modern science. No one can say with certainty that a major earthquake in Southern California is imminent. A USC seismologist asked directly about the timing of the next major San Andreas event answered honestly. It could be today, tomorrow, in 10 years, or in 30. On geological timescales, those options are indistinguishable. But what the science can say, and what the research published this year says clearly, is that the fault systems of Southern California are operating at stress levels without modern precedent. The earthquake gate at Cajun Pass is effectively unlocked. The Garlock fault carries centuries of unspent energy, augmented by a 30% stress increase from Ridgecrest in 2019. The San Andreas has not ruptured in a major event since 1857, and today, for the first time in 26 years, something moved exactly where the two most dangerous of these systems meet. California's Shake Alert Early Warning System is operational statewide. It can provide seconds to tens of seconds of warning before destructive shaking arrives. Enough time to take cover, for trains to begin emergency braking, for surgical procedures to be paused, for industrial systems to shut down. Those seconds save lives, but they only work if people know the system exists and have already thought about what they will do when the alert arrives. The gap between what California's seismologists know about this risk and what the average Californian understands and has prepared for remains large. That gap is the real vulnerability. Not the geology, which is what it is, but the human response infrastructure built on top of it. The 4.2 at Frazier Park today is not the big one, but it struck a fault junction that the geological record says is capable of producing one. And in a year where the seismic news has been relentless, Venezuela, Japan, the Philippines, the Gulf of California, Northern California, it is one more data point in a sequence that geologists say is telling us something about the current state of California's fault systems. The ground is speaking. The question is whether anyone is listening. Subscribe and hit the bell, because the next update on California's fault systems could come before this video finishes loading on someone else's screen.